This is my Physics 2211 lab report on constant velocity. Here are the table of contents displaying what we will be talking about today. The purpose of this investigation is to observe and compare the change in position against time of an object pushed along a table without changing direction to a computational model of a point mass moving at constant velocity with the same time intervals and also not changing direction. Throughout this lab, we will be demonstrating and applying Newton's first and second law. The first law states that an object in motion or at rest will remain in motion or at rest unless acted on by an unbalanced force, while the second law states that the net external force acting on a system is equal to the change in momentum of the system divided by the time over which this momentum changes. To model Newton's laws in the computational model, we will be using GlowScript, and to track the movement of the experimental object, we will be using Tracker. A brief preview of the results. As expected, a linear line was plotted from the model data because of perfect conditions, while a not so linear line was plotted from the experimental conditions, though it was quite linear still. First, we will be explaining physics principles, Newton's laws. Newton's first law explains why an object can move at a constant velocity when the net force is equals to 0, while Newton's second law can be explained even further with the equation F net is equals to rate of change of momentum over rate of change of time, with momentum being p. So if we rearrange this equation to make rate of change of momentum the subject of the formula, we get that F net times t is equals to change in momentum, which is equals to final momentum minus initial momentum. And then this, if we rearrange it a bit further, this gives us the momentum update formula, which is final momentum is equal to initial momentum plus F net times time. Also note that momentum is equals to mass times velocity, and so if we substitute this into the momentum update formula, we get that mass times the final velocity is equals to mass times initial velocity plus F net times time. This gives us the velocity update formula if we divide the entire formula by mass, giving us that final velocity is equals to initial velocity plus F net divided by m times time. As shown in the velocity update formula, a change in velocity requires a change in the net force. Therefore, if the net force acting on the system is 0, the initial velocity is going to be equal to the final velocity. I use these laws for this investigation as they accurately explain why the objects can move at a constant velocity and what would deter an object from moving at a constant velocity. For the experiment, to investigate Newton's laws, I'll be using a roll of tape with a reasonably low amount of friction. I'll also be using my DEX table with a reasonably smooth surface. So for this experiment, the system is the roll of tape and the surroundings are the table and the air. I pushed the tape from rest to allow it to roll across the table at a somewhat constant velocity and took a video of its smooth motion along the table. Using Tracker, I analyzed the change in position of the tape frame by frame, 30 frames per second, over the whole time period. Here you can see the experiment taking place and the data being recorded in the table and the graph being drawn of the movement of the tape. The line looks somewhat linear, but not quite. This can be due to a few factors like air resistance or friction. To recreate this experiment in GlowScript, we will be using some data collected. The initial time in this experiment was 0, the total time 1.73 seconds. The initial position is as shown. The initial velocity, which is calculated using R2 minus R initial over T2 minus T initial, is as shown. And remember, the ball is only moving in the x-axis, therefore we're only using the x component for our calculation. To accurately recreate the experiment in the model, the computational model, I had to change some of the parameters. I changed the mass of the tape, I changed the x component of the ball's initial position, and the x component of the velocity as well. And I also set the initial time to 0. I made sure that the program only ran for 1.733 seconds, which is the total time. I set all the components of fnet to 0, and I ran the program to obtain the model results. This is the program that I ran. You can see the ball moving at constant velocity, the graph, and the results obtained, which are all linear. Putting the model data and the experimental data in a graph, I was able to compare these two graphs, and it actually can be seen that the experimental data graph is actually above the model data line. The model is linear because constant velocity was used, and it is assumed that there is no air resistance or friction. In the experimental graph, it's a bit more curved because there is air resistance and friction in the real world, and so the model cannot always accurately predict the real world situations because it is not accounting for air resistance and friction. To make the model more accurate, I will most likely use an Fnet of 0 because in the real world there are resistive and external forces acting on the roll of tape, and despite the flaws of this model, it accurately represents the movement of the roll of tape with a constant velocity. Some of the sources of error could be from the fact that I pushed the tape too hard, which may have caused it to accelerate, which may be the reason why the experimental graph is actually slightly above the model graph. Another source of error could be when I was inputting the tracker data. I didn't put the tracker points at the center of mass of the tape. And another source of error could be the outside forces affecting affecting the constant velocity. For further investigations and questions, what if the axes were flipped? If the axes were flipped, then the the tape would be moving in the negative direction, which would be downwards, and the slope of the graph would be negative in terms of position versus time. And also note that the resistive forces acting on the tape in the real experiment now it was definitely not zero, and these were not accurately reflected in the computational model of the experiments, as the perfect scenario isn't the case in the real world. While the computational model of the moving object at a constant velocity may not be able to completely and accurately represent the movement of the tape in the real world, it can act as a reference, not only how the movement can behave in perfect worlds, but as a point of comparison between these two worlds.